Oh man, you guys, partial fractions. What did you think about that section? It's a good one, isn't it? I'm gonna just do some examples for you. So let's get going with this right away. Let's do an example. So let's say we have something like this: x squared plus 4x plus 1, and I'm gonna go ahead and multiply. I'm gonna give you factored form just because. Let's start off with an example with factored form. And so you've read through the book, you know kind of the procedure. You should absolutely write down the procedure, the two procedures that they give you in the book in the boxes. So I think there are actually 3 procedures, right? If we have, no, 4 procedures since I'm looking. There's the summary on the very last page that's quite important. So the whole idea with partial fractions is you have to figure out what type of polynomials you basically have for your factors. So I'm going to take the integrand, okay, and I am going, oh, and partial, it's just such a lovely, it's just such a great method. I just, okay, I know, pretty much everything in calculus too, I get excited about, but let's look at all the factors we have. So we have 3 factors. We have x minus 1, x plus 1, and x plus 3. These are all linear because the x is raised to the first power, and there's no repeated factors, right? Because I don't have like x minus 1 squared or x plus 3 cubed or something. They all are single linear factors. So remember then we set this equal to some constant a over x minus 1 plus b over x plus 1, and then plus c all over x plus 3, okay? So I'm just going to rewrite this. I know that if I combined all these terms together, right, got a common denominator, and put them all together, I would be able to get here. I just don't know what a, b, and c are. So remember, whatever you put in the numerator, this guy right, these 3 right here, they must be one, the way I remember it is, it's 1 degree less than whatever type of factor you have. So I'm not talking about if the factor is repeated. I'm just, what is the factor itself is linear, and so that's a degree 1, right? Polynomial, that's how I think of it as. And so 1 degree less than that would be a degree 0 polynomial, meaning no x's, just constants. Okay, so what am I going to do? I'm going to clear fractions. So the way we clear fractions in this, wow, I wanted to get this down a little bit. I'm going to multiply everything by that common denominator, x plus 1. I'm not going to look at it times x plus 3. That's horrible notation. Same thing here. You don't have to show this every time. X plus 1. This is really, really bad notation. I can do that. You can't. So all of this is going to cancel right over here. So let's see what we're left with. So on the left-hand side, we're going to be left with x squared plus 4x plus 1. On the right-hand side, when I multiply all of this crap through to each one of these, this term right here, the x minus 1s are going to cancel. So I'm left with a times x plus 1, x plus 3. Then what is b going to be left with? Well, b will be left with the x plus 1 will cancel. So b is left with x minus 1 times x plus 3. And I'm going to need a little bit more room. I hope you can still see this. And then what is the c going to be left with? X minus 1, whoops, x plus 1, right? All right. So what you can do from here is you could, if you want to, you could go through and you could actually just FOIL that all out and do something that they call equate coefficients. And I believe that is how they showed you to do that. Pray, am I looking in the book? I believe that's how they show you to do it. Yeah, on that first, the key idea when they talk about the idea here. But I want to show you one example that is actually pretty, or one way to do this is that's actually pretty cool to do. So what I'm going to do first is I'm going to look at basically all of the x values that would make each of these factors 0. So I'm going to first look at, well, what if I let x equal 1? Okay, if x is 1, then I'm going to take this whole equation here and I'm going to see what happens. Because remember, this equation has to be true no matter what x is. That's the whole idea, right? This is an equality. So no matter what x is, because I know x is a polynomial, no matter what x is, this should be true. So if I let x equals 1, what's going to happen is we're going to have some stuff going to kind of cancel out. So if x equals 1 on the left-hand side here, I'm going to get 1 plus 4 plus 1, that's 6. if x equals 1 in this term right here, right, I get a times 2 times 4. And then all over here, now why did we use 1? Because now look at this whole term, I get b times 0, right? And then this whole thing right here, I get c times 0, so that just goes away. So right away I see that 6 equals a times 8. If I divide by 8, sorry, I have to have my a on the left-hand side. I know it doesn't matter. I see that a is 3/4. And look at that, we found what a is without having to FOIL all that out and combine like terms, which this is a pretty cool shortcut, I have to admit. I used to not like to do this shortcut because I don't know why. I was like a purist or something. I don't know. I like to put it in a matrix and use my calculator, but it's so much easier with this. Let's look and see if x is -1, which is that the second number that would make that term right there 0. If x is -1, I get 1 minus 4, which is -3, plus 1, which is a -2 on the left. This whole thing, this next term here goes to 0. Here I would get b times -2 times -1 plus 3 is a +2. And then here, that -1 is going to take that x plus 1 and go to 0. Okay. Oh, I love how it makes my zeros. Isn't that cool? So what am I left with? I'm left with -2 equals -4b. Divide by the -4 and I get b equals a +1/2. I love this method. It's so great. All right, and the last one, to find c, well, what's the last thing that I would let x be? I'm going to let x be a -3, right? That's the other term that would give me a 0. If I put a -3 here, I get 9 minus 12 plus 1. So 9 minus 12 is a -3 plus 1 is a -2. -3 would make this term 0, so that's 0. -3 would make this term 0, so that's 0. And then a -3 in here is plus c times -2 times -3 minus 1 is a -4. So we have a -2 then equals what, 8c? And so if I divide everything by 8, what do I get c to be? C is a -1/4. Okay. So let's take that information, and now that we know that these are our values for the constant, I can rewrite, this is going to get really small, but now I can come back and really small, and I can rewrite this whole thing right here using the fact that I know what a, b, and c are. Wow, a, b, and c right here. That's what I want. Okay, so a was the coefficient that kind of dealt with the 1 over x minus 1. So let's rewrite my integrand then. So I'm just going to rewrite this just because I like to make sure, I like to bring it all back together and really make sure I did all of that work, right, for my lovely math teacher to read, and she adores reading it. I do. I really like to, until you make mistakes. Just kidding. I even like it when you make mistakes. But sometimes it's nice for you to tell the reader what you're coming back to, right? And I'm actually going to put my equal sign. So I'm going to bring the integral that I started with, and because I know this is going to be long, I'm going to write this as, now I know that this is going to equal, that a was 3/4, right? So I have 3/4 over x minus 1, or I'm going to rewrite that as 3/4 times 1 over x minus 1. Okay, then that b was what, 1/2? So I have 1/2 over x plus 1, or I can make that 1/2 times 1 over x plus 1. The reason I'm doing that is because I know I'm going to be integrating this. And then I have a -1/4 times 1 over x plus 3, right? All dx. And now these are pretty simple. You could think of this as a u substitution. Like when I go through and actually take these antiderivatives, I would pull that 3/4 out. I would make these all separate integrals, right, with a dx on each one of them. I could say, let's let u equal x minus 1, and then du is dx. But because du is equal to dx, I actually don't need to worry about that too much. I'm just going to go ahead and make that the natural log of absolute value. Remember those absolute values, x minus 1. Over here, that becomes the natural log of x plus 1, absolute value, minus 1/4 natural log of absolute value, x plus 3. And then they, in your book, which I like this method here, they put plus k, because we already defined up here, right, that c was the constant that I used for partial fraction decomposition. I don't want my readers to get confused as to why in one place I have c as something and then in another place I have something else. So we'll just use k for that, you know, random constant that could have been in there. Isn't that a good time? That was a good time. Wasn't that a good time? I love doing partial fractions. I think they're so much fun. Okay, let's look at another one. All right. Another example of the partial fraction decomp. That's what you say if you want to be cool, you know, because us mathematicians are quite cool. So if you want to be cool among mathematicians, which I know is your goal, is you say partial fraction decomp. All right, now look at what we have here. So my rational function, I have 6x plus 7 over x plus 2 quantity squared. So what is my factor? My factor is linear, right? Because it's of degree 1, but it's a repeated linear factor. So remember the trick with this one, and this one's kind of cool, is you still want to do a on top, right? Because the factor itself is linear. The inside stuff is linear. I know if I FOILed this out to be a quadratic, but the factor inside is linear. So I want to do 1 degree less than that. 1 degree less than that would just be constant a. So I'm going to do a over x plus 2. But then what else could I possibly have? I could also possibly have another term that had x plus 2 quantity squared, right? Because if you notice the common denominator here, right, these both go into that evenly. So that's kind of the trick when you're dealing with those repeated linear factors. So I'm going to multiply both sides. I'm going to multiply everything by the common denominator, which in this case is the x plus 2 quantity squared. Oh, I don't know what happened there. I'm not going to worry about it. Those cancel. So on the left, that's the whole reason you did it. I get 6x plus 7 equals, one of the x plus 2's cancel, so I'm left with a times x plus 2, right? And then if these cancel here, this is just plus b. Okay. Some ways you could do this. So you could let x equal -2. That would be a quick way to find b. That'd be a pretty easy way to find b. Another thing that you can do is equate coefficients. I would probably just go ahead and equate coefficients in something like this. So I'm going to take the a through. I think that's kind of the easiest in this case. And so notice for these, we're saying that these two polynomials are equal. So how many x's do I have on this side? I have a of them. How many x's do I have on this side? I have 6 of them. So for these to be equal, a had better be 6, right? And then in this case, what is my constant on this side? It's 7. What's my constant in this side? It's 2a plus b. So I know that 2a plus b must equal 7 for these polynomials to be equal. I know that a is 2. So 12 plus b must be 7. So it looks like with that 12, it looks like b must be -5. All right. So again, I'm going to let my reader know what I'm doing. I'm coming back to my original integrand, 6x plus 7 all over x plus 2 quantity squared dx. Notice how I'm putting my integral because I haven't actually done any calculus yet. I'm just doing algebra. And I remember I was at a conference once and someone was like, do not say it's just algebra, because that implies that algebra is trivial or that it couldn't be the difficult part of a problem. And that is so true. I had a professor in graduate school that was one of my advisors. Well, wasn't my advisor, but was on my thesis committee. And he was like, calculus is easy. It's the algebra that's hard. And that's so, so true. It's the algebra that's hard. All right, guys, so look at what's going to happen here. I am going to split this one up a little bit just so you can kind of see, because I want you to understand that natural log is not always going to be the thing that you're going to have. Because right here, this is not the natural log, you guys. Remember, natural log is 1 over the stuff. This isn't 1 over the stuff. This is 1 over something squared. So this really is x plus 2 to the -2. This one's going to be the power rule. So be careful about just blindly putting in natural logs and thinking that that's always what you're going to have, because that's not necessarily what you're always going to have. This then becomes 6 natural log of absolute value of x plus 2. That one's all right. Here, this is -5. This is going to be x plus 2 to the -1 divided by -1. Now, why do I know I can do that? Why do I know I could use C here also, by the way, since I didn't use C up here? Why do I know I can do that without that, even though it's not just x? Well, because if I could let u equal x plus 2, but notice du is just dx, so I don't actually have anything that I'm off by, right? So I'm just going to go ahead and do the power rule. So, oh no. Sorry about that. I was a little dramatic about that too. I had to go back and find all my work. So I have 6 natural log of absolute value x plus 2. That becomes a plus. And so then I can just put plus 5 over x plus 2, all plus some constant k. And typically that should be a capital K. Good. Let's do just like maybe 2 more just to kind of see other possible scenarios that could occur, and then we will call it good. So let's look at one where maybe we have a quadratic factor as opposed to a linear factor. All right, let's look at this doozy. Let's see what's going to happen here. So first I need to factor the denominator to figure out what type of factors I have, right? This is not irreducible. Clearly, irreducible means it can't be factored at all. I can take an x out. If I take an x out, I would be left with x to the 4th plus 2x squared plus 1. And this guy right here actually isn't irreducible either. Look at this one. If I could factor this. I could have plus 1 and plus 1. And then what would I multiply together to get x to the 4th? X squared times x squared is x to the 4th. And then when you do the outside and inside of FOIL, you see you get that 2x squared. Whoa, I don't know why I just erased that. I didn't mean to. Whoops. All right, and so what do we get? Actually, the integral now that we have is dx all over x times x squared plus 1 quantity squared. All right, so let's see what we're going to do with that. So I'm going to take, this is basically 1 over x times x squared plus 1 quantity squared. So let's look at the type of factors we have, right? So this first factor right here is linear. So that guy's going to just get an a over x, okay? Then let's look at our next factor. The factor inside here is a quadratic, you guys. So I always have to, the numerator always has to be the most general form of a polynomial that's 1 degree less than it. So the most general form, I can't use a again, is a linear. So I would use bx plus c all over x squared plus 1, right? That's the most general form for a linear. Now I need one more, dx plus e all over x squared plus 1, because it's a repeated linear factor. So remember, anytime you have a repeated factor, I have to have a fraction for each one of those. If that had been x squared plus 1 cubed, I would put in plus fx plus abcefg fx plus g all over x squared plus 1 cubed, okay? Oh man, this is going to be some serious algebra. I might have to cheat and just kind of tell you what it is. But all right, let's see what we're going to get here. So I'm going to multiply all of this by x times x squared plus 1 squared, x times x squared plus 1 squared. Those will cancel. That's why we did it. So I get 1 equals, here I'm going to get a times x squared plus 1 squared, right? Because the x cancel. Then I'm going to have plus bx plus c times one of the x squareds plus 1 will cancel, x times x squared plus 1. And then here just the, oh, this won't be too bad. Just the x stays. And now this one, if you notice, I can't use that trick of letting x go to a number and it going to 0 because there's no number. I could maybe let x equals 0 and I could figure out what a is. But if you notice, there's no number that actually makes x squared plus 1 equal to 0. So we're going to multiply this out. I'm excited too. I know. So I know what this guy is right here. I know that that guy is x to the 4th plus 2x squared plus 1. So if I multiply that by a, I get ax to the 4th plus 2ax squared plus a. If I multiply these two together, I get x cubed plus x, right? And then I'm going to go ahead and FOIL that with bx plus c. So first would give me bx to the 4th. Outside would give me plus bx squared. Inside would give me plus cx cubed. Hold on. Cx cubed. Oh man. And then last, I believe, would give me cx. Check me on that, guys. And then plus dx squared. You're like, you're the teacher, Sarah. Plus ex. Oh my goodness. All right, so I'm going to combine like terms. So my x to the 4th, I have an a and a b.
And then that's going to be times x to the fourth. What about, do I have any x cubes? I do. I think that's the only one. So plus cx, oh, it does not, it thinks my c's are zeros. Cx cubed, right? So I've taken care of that. I've taken care of that. I've taken care of that. What about my squares? I have a 2a, I have a b, and I have a d. So plus 2a, b, and d, x squared, right? I took care of those. What about any x terms? I have an e plus ex, and then my constant terms are a and c. And so I like to group those together. All right. So I know that looked like a lot of work, but actually to solve this, it isn't going to be too bad. So look at what I have equal to. On the left-hand side, my polynomial is 1. So if I want this to be equal, right? If on the left-hand side, I have 1. On the right-hand side, I have a plus b times x to the fourth. So how many x to the fourth should I have on the right-hand side? I think I may have said left-hand side there. I shouldn't have any. So I know a plus b must be 0. What about the x cubes? I shouldn't have any. So I know that, oh my goodness, c must equal 0, right? What about the x squareds? Well, I shouldn't have any. So I know that 2a plus b plus d should equal 0. And then finally, what about the x's? Also, I shouldn't have any. So e must be 0. That's really nice. That's going to be really nice for when we take the antiderivative. And then finally, for my constant term, should I have a constant? Yes, we should have a constant. That should be 1. Okay. All right. I know c is 0. So what does that imply about this guy? That implies that a equals 1. Okay. If a equals 1, right, then that implies 1 plus b equals 0, which implies that b is negative 1. So here's what I've got so far. I know a is 1. I know b is negative 1. I know c is 0. I know e is 0. So now what do I just need to find? I need to find d, it looks like. So from here, oh wow, I don't want to use that. From here, a is 1. So this will be 2. B is negative 1 minus 1 plus d equals 0. So it looks to me like d is also negative 1. So d is negative 1, and again, e is 0. Whew. Okay, so let's go back to what we had. Look at what we had up here. I'm going to put those all into here, and I'm going to go ahead and do my integral. Okay, we're almost done. I think this will probably be my last example. So my dx all over x times x squared plus 1 quantity squared, right, is going to equal, all right, so I have the integral of 1 over x, right, and then it was bx plus c. The c is 0, so I have a negative x all over x squared plus 1. And then I had dx plus e, so plus, again, a negative x all over x squared plus 1 quantity squared dx. Awesome. All right, let's start taking these antiderivatives. So I'm going to use good notation here. I know this is a lot of writing. You can handle it. I know you can. I'm going to take the natural log absolute value of x, right? Here I'm going to have minus the integral of, notice I have x over x squared plus 1. So what I'm going to do here is I'm going to do u substitution. I'm going to let u equal x squared plus 1, right? What does du equal then? It'd be 2x dx, so I'm off by 1/2. So I'm going to have 1/2 times 1 over u, and now I have a du. Same thing is going to happen here. I'm going to let u equal x squared plus 1. Again, du is going to be 2x dx. So what do I get? I get 1/2 over, but now instead of just 1 over u, I have 1 over u squared du. Okay, so notice sometimes it's not always just natural log. I'm using good notation, so I'm bringing down that natural log absolute value of x. This is going to be minus 1/2. Antiderivative of 1 over u is the natural log absolute value of u. We'll come back to that u here in a minute. Here also I have 1/2. This is u to the negative 2, so that's going to be times u to the negative 1 divided by negative 1, all plus some k. Oh my goodness, we're almost done, I promise, I promise. All right, so natural log, absolute value of x. What is u? U in this case is x squared plus 1. So you know what I can actually do? I'm going to be so bold as to just make this
Nope, I'm not gonna make it that. I'm not gonna worry about the absolute value. Why don't I have to worry about the absolute value? Why? Why, people? Yes, you're correct, because x squared plus 1 is always positive, right? And then that u goes in the bottom, so I'm gonna have plus 1 over 2 times x squared plus 1, and then this whole thing is plus. Okay, that was a good time. You know, if you want, also you could do some logarithm properties and like combine those and stuff if you would like, but I don't know, you don't have to do that. I hope that helps a little bit to figure out how to do this. Listen, if you want to do some of these, I don't know if it's really worth the time or not. These, you know, solving for these, you sure could put this in a matrix in your calculator, in your graphing calculator. If you guys are interested in me showing you that, I sure can record you a quick lecture on how to put these into a matrix. And finding, you know, solving this using, if you have a graphing calculator and you have the ability to do a matrix, we sure could do that. Just let me know. If not, the algebra on it is not going to be so difficult that you can't do it without a calculator, the ones that you're given. So, and the ones that I give you, like, whoops, on a test or something will not be difficult, so difficult that you have to use a calculator. All right, you guys, that was a good time. Let me know if you have any questions.